Thank you, Kurt. So we previously got a lot of advanced questions about homomorphic encryption and how can one optimize it, how can one make it more efficient, and we somewhat kind of deferred those questions and gave very brief answers. And this particular problem that Sasha described is actually a great, in my opinion, quite complex example that, for instance, one of the solutions involves logistic regression training as a subroutine to discuss some of those techniques, advanced techniques, some of those design decisions that one has to basically go through to develop an efficient homomorphic encryption solution. So basically in this talk, what I'll try to do is I'll try to come up with certain best practices that actually apply to, I mean, almost all of them apply to this study, and talk a little bit about them. Okay, so prerequisites for this talk. And Kurt, I assume everything, I mean, the presentation is coming up fine, right? So you can see that the slides are—
Yeah, loud and clear, and everything is in the open, so all good. Thank you.
Okay, thank you, Kurt. So I suggest, so since this webinar will be recorded, that to those people watching it later, I suggest watching Sasha's talk just to get familiar with the genomic application. I also suggest getting familiar with the approximate homomorphic encryption, CGKS, the talk that basically we had 1 month ago. And of course, other webinars are always helpful to get a more complete picture on homomorphic encryption. So the agenda here, I mean, it's relatively short, but there are a lot of concepts that it includes. So we're going to go over certain data science guidelines of how one builds an efficient homomorphic encryption solution. We're going to go over some of the data encoding challenges that and some of the decisions which are fundamental, I mean, to get practical efficiency. We're going to talk about some, I would say, like compiler-like optimizations that one has to go through as well, and also system-level optimization. So this particular work actually combined all 4 of those groups of improvements, optimizations, design considerations. So it's actually a great example that we can use to explain those. So the data science guidelines. So everything starts, I mean, we don't just go into PALISADE and start writing the code, writing efficient homomorphic encryption solution. The first step that one has to basically take is to actually develop an efficient data science algorithm that can solve this problem. Like in this case, we're talking about the GWAS problem. And the requirements for this algorithm may be quite different from what one deals basically in the conventional domain in the clear. For instance, in the case of homomorphic encryption, we have to be mindful of the multiplicative depth. That's a very important consideration that determines the efficiency of the computation. And so this is something that one has to go through, is to examine the various approaches that exist in the basically, let's say, conventional data science or in genomics, and see which of those approaches would minimize the multiplicative depth. And it's also related to this. Typically, parallelizable workflows are preferred over sequential ones, because if something is parallelizable, you can use a smaller depth and basically some redundancy. And when one deals with sequential approaches, when you have to do a lot of computations in a series, that basically means most likely the depth will be large, and the efficiency and for instance, the runtime of this computation will be significantly longer. So this is a major design exercise one has to go through. And of course, data science and genomics expertise is needed. So for example, in this work, we had Sasha, who is one of the leading experts in the field of genomics, Marcella, who is one of the leading experts in data science, and also we had some expertise on the HE side. So this is a very important aspect to keep in mind. Then another consideration that basically we had when designing those algorithms is what algorithms minimize the operations that are challenging for homomorphic encryption. I mean, when we say challenging, they basically are their efficiency. I mean, they require extensive, basically computational resources and a lot of runtime or storage. Almost every operation can be performed with homomorphic encryption, but the question of efficiency, I mean, how efficient they are. And for instance, comparisons are typically quite challenging, and while they can be done, but one tries to minimize them. So this is also another consideration that we basically we're keeping in mind when designing the algorithms. The other side, and we discussed it in the prior webinars on approximate homomorphic encryption, on integer homomorphic encryption, is the ability, the SIMD capability, the ability to pack vectors of numbers into a single ciphertext. So there is this inherent parallelization capability that homomorphic encryption has, and whenever we design algorithms, we have to take advantage of that. So it's very important to be able to work with vectors, for example, of or matrices of numbers to get the best performance throughput in homomorphic encryption. So related to SIMD, for instance, another consideration is the operations. Since we're dealing with a vector, we need to introduce rotations, and rotations are typically relatively expensive. So we try to minimize the number of rotations. And in all this, there is another extra consideration about the information leakage. So one approach is to do the full computation using homomorphic encryption. The other is to do, for example, some pre-processing and also some post-processing after the result is decrypted. And whether this is acceptable for a given application, that's certainly, I mean, a question that should be considered. For instance, if some information can be leaked, I mean, and it's not, I mean, it would not cause any issues with basically related to privacy concerns, then one has to wait. I mean, do we want to apply homomorphic encryption, or do we want just to do it as part of post-processing? So all of those had to be considered. So another important consideration is a lot of work, and specifically for this genomic application, was done before the first line of basically C++ code in PALISADE was written. And we essentially experimented with different data science algorithms using standard data science packages, I mean, such as R, etc., and tried to assess which algorithms would give us, for example, what quality we would expect for certain algorithms if we use certain approximation techniques and so on. So, and we look at certain metrics which we know will propagate to the encrypted domain as well. And like in CKKS, in the approximate homomorphic encryption, we know that output precision is something that's important when we get a result, and how many bits of precision we get. But in reality, for many data science applications, statistical applications, or regression training applications, that's not always the right metric. It's essentially, we need to look at the quality and parameters such as area under curve and so on. So this is also an important consideration, is that we're trying to solve a problem, and we're going to use, we have some limitations, I mean, in terms of the techniques that homomorphic encryption can do faster or slower. And we have to keep this in mind when we're designing. And just as an example from Sasha's talk, so we considered two algorithms, and one of them was a statistical one, and the other is based on logistic regression training. So for the statistical one, which was able to satisfy these quality metrics that were set and matched the previous secure multi-party study, we picked specifically the chi-square test. I mean, obviously, we know that it works and it's relevant in this genomic domain. But in addition to that, it only requires a multiplicative depth of 3, which is considered a very shallow circuit. All operations, the way we design it, are SIMD friendly. So we're taking full advantage of the packing capability. And basically, this particular algorithms avoided, for instance, comparisons and some harder operations. So so a lot of work basically happens at the data science and algorithmic level, which is very, very important and will determine how practical the solution is. So the second question, so Kurt, I don't know if there are no questions for this part, I'll continue. But if there are questions, please feel free to interrupt me.
Yeah, no questions have come in so far, but none yet. And hopefully there will be as we go. And as there are questions, of course, I'll give you a slight nudge, Yuriy, so we can address them as we work through, of course.
Mm-hmm. Thank you, Kurt. So the other very important question is related to data encoding optimizations. So we mentioned this SIMD capability, packing capability, and it's very fundamental and very often in both statistical and let's say regression training approaches, we deal with some form of matrix arithmetic, and we need to find ways to pack these matrices into ciphertexts, basically that support SIMD operations in a way that minimizes the complexity, of computation. So just as an example, in this particular work, we considered different formats. You can think of it as row-wise and column-wise of representing and packing matrices, where we introduce some cloning or replication of values to essentially support efficient matrix arithmetic, matrix products. And this was a very important part. So we had to be smart about how we're going to encode X, for example, the transpose of X, and in this case, the vector Y, basically the typical parameters of any regression training problem. So this is a lot of work went into identifying the packing that makes sense, and basically that's what we did. And then for part of the algorithm, we used this type of encoding. Then when we transitioned to another part of the logistic regression training algorithm, we switched to slightly different encoding, packed integer encoding, where the same values are cloned to all slots. So quite a few of our optimizations were basically around, okay, where do we keep working with this packed matrix encoding? At which point do we switch to the other encoding, and what's the cost of it? And basically, the conversion was the main bottleneck of our logistic regression training solution. And it's extremely important to understand that the right methods of this data encoding can dramatically reduce the cost of matrix arithmetic. So this is also, we can think of it as somewhat additional work on the data science side. So how do we encode? How do we represent the matrices that we work with? So this was a very important part of our work. So now so far everything has been somewhat on the data science level. Now we're going to go into homomorphic encryption specifics, and what's very important in homomorphic encryption is basically reordering the certain operations that we use to get the best results. So you can think of it as similar to the types of optimizations a compiler typically has to do. They're very relevant in designing a efficient, let's say, CKKS implementation in this case for the problem. And when basically, as a starting point for this analysis of operation reordering, for instance, we have to bear in mind that there are two bottleneck operations in essentially almost any computation based on CKKS. One of them is key switching. That's in almost every case that we considered, maybe except for the chi-square solution in this case, because we were able to completely eliminate key switching operations. But typically, key switching operations are the bottleneck operations, and we either try to minimize them, and in the case of chi-square, we were able to completely eliminate them, or we're trying to reduce them. And these key switching operations are typically performed after multiplications and rotations. And just for the terminology's sake, key switching after multiplication is called relinearization. And then there is another important operation, rescaling, which we discussed in detail in the webinar on approximate homomorphic encryption, basically something that allows us to scale down the numbers, encrypted numbers, to remove least significant bits. That also has a significant cost. Both of them under the hood use so-called number-theoretic transforms, which are the lowest level, I mean, almost the lowest level bottlenecks in any homomorphic encryption computation. So some of the techniques that we considered in our work is to apply so-called lazy realization and lazy rescaling. So the idea is that instead of just using the standard protocol, you do multiplication, then you do realization, and then rescaling, we can often delay realization and, for instance, rescaling until a later stage. And as an example, if we need to multiply a lot of ciphertexts and then we need to add them up, we, instead of performing realization and for each multiplication, we can just do it at the end. So we can delay the realization until the very end, and perform this basically multiplication of many ciphertexts in addition at the cost of a single realization. And very similar ideas apply to rescaling. So like just the example that I just described. So it's important. So sometimes we can delay certain operations, put them further out, and this will give us certain benefits. Then another optimization that we considered in this work is related to the use of so-called fast rotations. So there is a I'll refer to it as a slow rotation or normal rotation, a rotation that always requires a full key switching operation after it. It's by itself, it's quite expensive, but there is also a type of fast rotation when we need to perform multiple rotations of the same ciphertext. We can pre-compute a very expensive part of key switching, or multiple expensive parts of key switching, and do them only once. And under the hood, it works basically by rearranging how, for instance, the so-called operation of automorphism is done within a rotation. So rotation by itself includes several subroutines, and we rearrange the subroutines using certain linear properties to achieve that. So an important consideration was to rewrite our algorithm so we can have as many as possible of fast rotations versus slow rotations. So this is something that we did as part of this work as well. Then another consideration is the use of technique binary tree multiplication, which minimizes the depth, and that's a common technique, and we of course use it in this work. If we need to perform a chain product of a large number of ciphertexts, it's better to do it in a binary tree manner so that the depth would be basically logarithmic to the number of multiplication needed. And yet another optimization that we considered in this work is, for instance, if we have loops and we perform, and they're performed sequentially, typically that increases the multiplicative depth, and which keeps growing. But very often we can either use closed form expressions or unroll loops to basically reduce the effective depth that's needed. And we certainly used this technique heavily for both the chi-square and logistic regression training solution. And I mean, just yet another example is that as we discussed previously, rotations are quite expensive. And sometimes we can replace them with fast rotations. Sometimes we can replace a certain rotation with a summation over a vector, basically, and use additions, which are very cheap instead of rotations. So these are the various considerations that I would basically call like compiler-like. So this is, and there is also active research in this field to try to automate some of these optimizations. And certainly this type of techniques helps speed up, and develop practical solutions based on homomorphic encryption. And so this is
yeah, sorry. Yeah, let me just step in here for a question. There was a question that came in from Christian, is that in the packing approach, the operation between slots aren't really too expensive. How could one speed up the operations between slots?
The operations between slots. So maybe I'll try. I'll try to elaborate further to understand. So typically, all operations are performed at the level of vectors. So we can, I mean, for efficiency's sake, so we can take advantage of SIMD. So, and the idea is that if we were to start working with basically per slot operation, that will become very expensive. That's, you know, the idea is that we want to batch them together and take advantage of SIMD. So that was one important requirement in the encodings that we discussed, is how do we basically keep at the highest level possible, the highest level of batching possible. And the rotation, so there are very cheap operations that trivially basically work with those vectors, which are addition and multiplication. They're component-wise. It's just you need a single ciphertext multiplication or a single ciphertext addition. They're very trivial and easy to do. But the rotation part is basically when we need to move something to a certain slot, which, you know, for instance, is needed in matrix arithmetic. That is an expensive operation that basically exposes certain individual slots. And this is, and typically when we try to optimize, that's the consideration is, if we support a certain, let's say, matrix vector product, how do we minimize the number of rotations needed? So that's basically, I mean, those are the typical considerations. But maybe if there is a more advanced formulation or detailed formulation of the question, I'm happy to answer that as well.
Then there's a question that just came in. Does the PALISADE library include support for general purpose FHE compilers? And actually, our favorite subject, Yuriy, ramparts.
Okay, so yeah, maybe we'll split the the answer. So I'll basically give my perspective, and maybe you'll give yours, Kurt, especially on the rampart side. So I'm aware that there are certain compilers that are being built that interface with PALISADE, so that I've seen that in the literature. There is some work that our team did, and as part of Ramparts and Hector previously, which I mean, the Ramparts work was done very early and did not take full advantage of packing at the time. So I would not, basically rely on those techniques for let's say for the particular GWAS problem we just discussed. This was early work before compilers became popular, so it's, I mean, the simple way to say it, it's still an open problem, interesting problem, and we're definitely looking into this. But Kurt, I mean, if you could provide further, thoughts on your perspective.
Yeah, no, sure thing. We've been, both the PALISADE community and then Yuriy and I specifically have been looking at how we can make homomorphic crypto in general much easier to use to people who aren't schooled in the art of the actual low-level FHE operations and things like that. And there's a lot of different threads that are going on that we are involved with, and some that we are, the broader community is also pushing, including higher level libraries for data science and this notion of compilers. And as Yuriy mentioned, we did do a lot of early work with Ramparts. Ramparts was intended to be more of an R&D type activity to justify further work and a project that later was called Hector, that we were involved with and helped motivate. And there's been some follow-on to that for some later projects that we currently have, and also other work that's going on in the community for PALISADE. I know that there's been an active project with NYU and the team at NYU that has basically integrated PALISADE into a high-level compiler and a few other projects that are very similar. And this is actually something that we're planning to have in a future webinar, and because I think it's a very nice active research engagement and shows with some of the broader ecosystem that goes into privacy protected computation about homomorphic crypto and PALISADE being a building block in this. And this is, of course, a really interesting area for us, as might be implied by the conversation between Yuriy and myself right now. So it's a good question. It's very loaded. It's a lot of stuff there. but it's something that's very exciting to us too. Back to you, Yuriy.
Yeah, absolutely. Yeah, maybe I'll just add one minor comment to this, that in addition to looking into automated compiler approaches, we also try to automate as much as possible some of the lower level decisions in PALISADE. So that's something that, so the usability of PALISADE interface, that's something that was very important for us. For instance, in the previous webinar, we talked about CKKS, and there are different flavors of CKKS. So there is one that where you have to do everything basically manually, but I mean, and hypothetically, you can get the best efficiency, but it's either, you need to be a subject matter expert, or you need to use some automated compiler toolchain, or there is also alternative methods in CKKS that basically do the rescaling automatically, do various other things automatically, key switching automatically. There is a certain performance cost, but at least from the usability perspective, when you build something, it works out of the box, so that the compilers are not necessary to get, for example, the initial capability working or to get something usable. So it's, in other words, it's in my mind, it's basically multi-faceted, multi-level problem, just even like this slide implies, because there are also system-level optimizations. And that some of these issues can be addressed at the PALISADE level, which we're trying to do. Some of them would benefit from a compiler. Some of them would benefit from, let's say, special data science tools that are HE friendly. And some of them are just like system level optimization. So just to give a broader perspective on this. Okay, Kurt, so shall we continue?
Yes, let's, please.
Sure. So now the fourth basically group of optimizations that we considered in this paper, which I labeled as system level optimizations. So the first one is totally understandable, multi-threading. So PALISADE does support multi-threading using OMP, and typically the best parallelization can be achieved the closer you are to the actual application level, so at the highest levels. So we certainly use various loop parallelization techniques, some of them that are already built in PALISADE, some of them that we added at the application layer to get the best performance in a multi-threaded environment. So the other consideration is related to serialization, deserialization. So in certain applications, we may need relatively large data structures with keys and ciphertext. And it's important to optimize serialization to basically reduce the RAM requirement. So if you have a large data structure composed of, let's say, a bunch of ciphertext, it's better to serialize ciphertext at a time and deserialize to minimize RAM if that's needed. So that, of course, the main constraint here, are we dealing with a RAM constrained environment or not? For instance, approximate homomorphic encryption is a leveled scheme, and the further you are in the computation, the smaller is the effective basically size of integers, I mean, of the actual ciphertext that you work with. And sometimes if you need a ciphertext at a later time, not at the very beginning, you can encrypt the ciphertext at this smaller level, so which would reduce both storage and computational complexity. Then another technique that we also applied in the logistic regression training prototype is essentially related to the size of evaluation keys. So there is an initial size which is the biggest, but as we perform the computation, it's especially leveled computation, one can compress the evaluation keys and again reducing both storage and runtime. So yet another technique that one can consider is in certain techniques such as linear transforms, there are different ways to basically perform them, and there are different trade-offs, and very often limiting factor is the number of rotation keys. So, and for instance, in some scenarios, one can use a larger number of rotation keys but get better runtime. In other, or alternatively, a smaller number of rotation keys can be used, but at the expense of increased runtime. So depending on the system we're dealing with, whether it's memory constraint or basically compute constraint, we can basically make those decisions. Then something that we also considered in this work, I mean, at least some initial elements, is how do you distribute a computation, for instance. And of course, then in that case, there are additional considerations such as related to communication costs. So these are various system level issues, which are, I would say, they're not unique to homomorphic encryption. So you could probably apply them to any other crypto problem or a crypto protocol. I mean, most, at least some of them. But they're still very important in getting practical efficiency. So this is, they're not algorithmic, they're not like compiler level optimizations, but they do change the actual runtime or RAM utilization that you see in practice. And this is basically concludes the discussion of various optimizations. It was hard to get into more detail for each of them, but we wanted to present various best practices that we find useful when designing those efficient applications. I mean, using when designing homomorphic encryption solutions for actual applications. So regarding the particular problem that Sasha discussed, the genomic analysis, secure genomic analysis. So the source code for this problem is available, so I'm providing the link here. So if someone wants to look at how we address some of those challenges. So the PNAS paper is also available source, especially the appendix. So that's so the link here is provided, and there's additional information available in our earlier I-2018 paper, which basically focused on the logistic regression solution. So for essentially these two papers and the source code provide more technical information that was discussed both in Sasha's presentation and mine. Okay. Thank you.
Great. Well, Yuriy, thank you very much. And Sasha, thank you very much also. We'll pause here if there are any more questions. Okay, well, I'll plug that this is, of course, not an one and done collaboration. It's very much an ongoing set of activities that we have going on. And as we always like to say, the best is yet to come. Well, Sasha, thank you again for your time, and thank you again for laying all this out for those of us in the PALISADE community who want to know more about these applications. And Yuriy, thank you again for laying out the technical work and the crypto that's been going to support the application.
Thanks a lot, and thanks for inviting me. This was really fun, and I agree. Lots more cool stuff happening. Hopefully, we'll have more to talk about soon.
All good. Any last words, gentlemen?
Thanks.
Okay. Well, thank you again for our attendees, and we will send out further email where we have recorded this presentation. We'll be posting it on YouTube for later reference, and we'll have links to this on our PALISADE website. Well, thank you again. And
Kurt, I'll just add one more remark that will also include the slides for both presentations.
Good, all good. All right, thanks again, everyone. Have a great day. Have a great weekend. Bye.
Bye.